Good morning, students. Today we will discuss various methods of obtaining topologies on a given set. So the first method of obtaining a topology on a given set is by using the properties of closed sets, which we already discussed. So let us take X be a non-empty set and alpha be the collection of all those subsets of X which satisfies the following conditions. First property, phi belongs to alpha. Here phi is the empty set that belongs to the collection alpha. Second property, X belongs to alpha. Third property, if we take any arbitrary collection AI such that each AI belongs to alpha for every I belonging to the index set, then the intersection also belongs to alpha. It means arbitrary intersection of members taken from alpha again belongs to alpha. The fourth property, if we take two members from alpha, A and B, then their union also belongs to alpha. We are given these four properties of the collection alpha, and we are to prove that there exists a unique topology on the set X such that this alpha is nothing but the collection of all the closed sets with respect to topology top. So in order to find a topology, let us define a collection top, the collection of all those subsets of X whose complement belongs to the collection alpha. Complement of A means X minus A. So in this way we have defined a collection. Now we prove that this collection defined by this equation is a topology on the set X. Now let us verify the conditions for being a topology. The first condition, we have to check that phi belongs to tau. Now phi belongs to tau if its complement belongs to alpha. So let us find the complement of phi. Now complement of phi means X minus phi. X minus phi is X and X already belongs to alpha. So by definition of this collection, we can say that phi belongs to tau. So we have verified the first condition. Next we check X belongs to this collection tau. For this we have to check that the complement of X belongs to alpha. Now complement of X means X minus X and X minus X is phi, and by the properties of collection alpha, phi belongs to alpha. So this proves that X belongs to tau. In the third condition, let us take I belongs to index set, be an arbitrary collection of members from tau, and we have to prove that the arbitrary union belongs to tau. Now this will belong to tau if its complement belongs to alpha. So let us find its complement. Its complement is obtained by using De Morgan's law. By De Morgan's law, X minus union AI is equal to the intersection of the complements of AIs. Now, because each AI belongs to tau, so by definition of tau, their complements belongs to alpha. Now, by the properties of alpha, arbitrary intersection of members from alpha again belongs to alpha. So their intersection will again belong to alpha. And because this is equal to X minus union AI, so we can say that X minus union AI belongs to alpha. It means complement of this union belongs to alpha. So by definition, union I belongs to index set. This belongs to tau. Now, let us verify the last condition for being a topology. For that, let us take A and B, two members from tau, and we have to prove that their intersection again belongs to tau. Now because A belongs to tau, so by definition of tau, its complement belongs to alpha. It means x minus A belongs to alpha. B belongs to tau, so complement of B belongs to alpha. Complement of B means x minus B. Now x minus A and x minus B both belongs to alpha. Now by properties of alpha, which we are given in the statement, their finite union, that will also belong to alpha. So complement of A union complement of B belongs to alpha, and by De Morgan's law, this is equal to the complement of A intersection B. So we have proved complement of A intersection B belongs to alpha. So by definition, we can say that A intersection B belongs to tau. So till yet we have proved that the collection tau defined by us, that is a topology on the set X. So this proves the first step of the theorem. In the next step, we prove that the collection alpha is nothing but the collection of all the tau closed sets. Tau closed sets means which are closed with respect to the topology tau. So let us take alpha 1 be the collection of all those sets which are closed with respect to the topology tau. We have to prove that alpha 1 is same as the given collection alpha. So let us take A belongs to alpha. Now A belongs to alpha if and only if its complement belongs to tau. Now because x minus A belongs to tau, it means x minus A is open with respect to topology tau. So from here, if and only if A is tau closed. Now the collection of tau closed sets, that is alpha 1. So from here we get A belongs to alpha 1. So A belongs to alpha if and only if A belongs to the collection alpha 1. So this proves that alpha is nothing but the collection of all the closed sets with respect to the topology tau. And in the last part, we prove the uniqueness of this topology tau. So in order to prove that this topology is unique, let us consider another topology, tau star on the set X, such that the given collection alpha is same as the collection of all the closed sets with respect to the topology tau star. Now alpha is equal to alpha 1 star and also alpha is equal to alpha 1. So we can combine the two. We get alpha is equal to alpha 1 is equal to alpha 1 star. These three collections are same. Alpha is a given collection. Alpha 1 is the collection of tau closed sets. Alpha 1 star is the collection of tau star closed sets. Now we are to prove that the two topologies are same. So let us take G belongs to topology tau. By definition, G is tau open. So if a set is open, its complement is closed. So X minus G will be closed, tau closed. And all the tau closed sets are in the collection alpha 1. So from here we have X minus G belongs to alpha 1. Now alpha 1 is same as alpha and alpha is same as alpha 1 star. So we get X minus G belongs to alpha 1 star. It means X minus G is closed with respect to the topology tau star. And so its complement will be open with respect to topology tau star. So G belongs to tau star. Proceeding in the reverse steps, in the same way we can prove the converse also, and combining the two parts we get tau is equal to tau star. So this gives the method of obtaining a topology by using the properties of closed sets. Now the next method is the method of obtaining a topology by using the properties of neighborhood system. The properties of neighborhood system we have already discussed. We will use those properties to find a topology on a given non-empty set. So let us take X be a non-empty set, and for each X belonging to the set X, Vx is a non-empty collection of subsets of X. and this collection satisfies the following properties. First property, X belongs to A for every A belonging to this collection. Means every member of this collection will contain X. Second property, if A belongs to the collection Vx and A is subset of B, then B also belongs to the collection Vx. It means superset of A also belongs to the same collection. In the third property, we are given that if A and B are two members from the given collection, then their intersection also belongs to the collection Vx. And the last property we are given, for each member A belonging to the given collection, there exists some member belonging to the same collection which is contained in A, and this G belongs to Vy for every Y belonging to G. We are given these four properties of the collection Vx, and we are to prove that by using these four properties of the collection Vx, there exists a unique topology tau on the given set X such that this collection Vx is nothing but the neighborhood system of the point X with respect to the topology tau. So, first of all, let us define a collection tau which is to be proved to be a topology on X. So let us take the collection of all those subsets of X such that A belongs to Vx for every X belonging to A. It means whenever X belongs to A, this implies that A belongs to Vx. If this condition is satisfied, then we say that A belongs to the collection tau. And we are to prove that this tau is a topology on the set X. Now by definition, phi already belongs to tau, and now we show that X belongs to tau. Let us take X belongs to X, and we are to prove that X belongs to Vx. Now because the collection Vx is non-empty, so we can take some member A belonging to this collection. Now because A is subset of X, and in the second condition we are given that if A is subset of B, then B belongs to the collection Vx. Now here A belongs to Vx and X is superset of A, so by second given property X belongs to the collection Vx, and this proves that X belongs to tau. In the third property, let us take an arbitrary collection AI such that each AI belongs to the collection tau, and let us take A is the arbitrary union of the members of this collection. We are to prove that this A belongs to the topology collection tau. We are to prove that. So let us take an element X belongs to A, and we are to prove that A belongs to the collection Vx. Now because X belongs to A, it means X belongs to union AI. Now because X belongs to union AI, so there exists some index J belonging to the set of index numbers such that X belongs to AJ. Now because this AJ, that is a member of collection tau, so AJ belongs to tau and also X belongs to AJ. So by definition, we can say that this AJ belongs to the given collection Vx, and also AJ is contained in A, and by using the second property, if this set is in the collection Vx and then its superset also belongs to collection Vx. So we have proved A belongs to Vx for X belonging to A, and by definition we can say that A belongs to the collection tau. In the last property, let us take two members A and B belonging to the collection tau, and we are to prove that their intersection belongs to tau. If A intersection B is phi, then clearly it belongs to tau. So let us take the case when this intersection is non-empty. So let us take an element from this intersection. Now by definition of intersection, it means x belongs to both. X belongs to A as well as x belongs to B. Now because x belongs to A and A belongs to tau, so by definition of tau, A belongs to the collection Vx. Again from here, x belongs to B and B belongs to the collection tau. So by definition of collection tau, B belongs to Vx. Now A belongs to Vx, B belongs to Vx. So by the third given property, their intersection also belongs to the collection Vx. Thus all the conditions for being a topology are satisfied. So we can say that the collection tau defined by us, that is a topology on the set X. Now in the next part, we claim that this given collection Vx is nothing but the collection of all the neighborhoods of point X with respect to the topology tau. Nx means tau neighborhood system of X. So in order to prove this, let us take a member A belonging to the given collection Vx. Now we use the fourth property of the collection Vx. According to that property, for A belonging to Vx, there exists some G belonging to the collection Vx such that X belongs to G is contained in A and G belongs to Vy for every Y belonging to G. Now because we have X belongs to G is contained in A and also G belongs to Vy for every Y belonging to G. So by this condition, we can say that G belongs to tau. Now combining the two conditions, we can say that A is neighborhood of X and therefore A belongs to the collection Nx. So we have proved A belongs to Vx is implying that A belongs to Nx. It means the collection Vx is contained in the collection Nx. And doing the same steps in the reverse, you can prove Nx is contained in the collection Vx. And combining the two, we get the collection Vx is same as the collection Nx. Now it remains the last step to prove the uniqueness of the topology. We have to prove that the topology tau is unique. So let us take another topology on the set X, and that topology we have denoted by tau star, such that the given collection Vx is nothing but the collection of all the neighborhoods of the point X with respect to the topology tau star. Now Vx is equal to Nx star and also Vx is equal to Nx. So we can say that the three collections are same. The given collection Vx, the tau neighborhood system of X and the tau star neighborhood system of X. These three are same. Now to prove tau is equal to tau star, let us take G belongs to tau. Now by definition of tau, G belongs to tau means G belongs to the collection Vx for every X belonging to G. But Vx is equal to Nx. So we can say that G belongs to Nx for every X belonging to G. Now Nx is same as Nx star. So G belongs to Nx star for every X belonging to G. So by definition, G belongs to tau star. So G belongs to tau implies that G belongs to tau star. So this proves that tau is contained in tau star. Reversing these steps, we can prove the reverse also, and combining the two, we get tau is equal to tau star. This proves the uniqueness of the topology tau. So this was the second method of obtaining a topology on a given set by using the properties of neighborhood system.